Hello and welcome back to possibly one of the trickier exercises you're going to do this year. Now, I want to tell you up front, with this particular exercise, it takes a lot of people quite some time to understand or to grasp the concept. The other thing is, if you don't get it first up, that's pretty normal. Don't stress. You still obviously have to try and come to terms with it, but don't stress, because everything from exercise 8.5 onwards, none of it depends on you having to actually have a solid understanding of this exercise. So you will need to understand it. I will put something like this in your test. However, not understanding it today doesn't mean that we can't go on and do 8.5 onwards, because 8.5 onwards, the next few exercises are all about how we can do this a far easier way using shortcuts. The way we're about to differentiate today is by first principles, the old-fashioned way, the more tricky and difficult way. So I know you're excited, I am. Let's go. Now, let's start by looking at just a graph. Doesn't really matter what the graph is. In this case, you may pick up that it's actually part of a parabola. This is actually y equals x squared, but that's not important. It's just a graph. So we can see on the graph, what I've done is I've got my graph, there's my parabola, and I've taken 2 points, just random points, and I chose these because they were fairly easy. I chose a point down here and I called it the point P, and it's at 1, 1. Up here I chose a point, I called it point A, and it's the point 4, 16, because I've gone out 4 units and up 16 units. Notice that the x-axis and the y-axis, the scales aren't quite the same. That's okay. How would I find the gradient of the line joining A and P? Well, I'm glad you asked. I think I'd use the gradient formula, and remember, that's y2 take y1 on x2 take x1. And because I've got the 2 points labelled P and A, I've written the gradient of PA. That means the line joining P to A. Now if I do y2 take y1, there's y2. I'm going to call that my second point. y2 take y1 over x2 take x1 gives me 16 take 1 over 4 take 1. Now 16 take 1 is 15, 4 take 1 is 3, 15 over 3 cancels to 5. We've found the gradient. We're actually doing calculus at the moment in a way, just not quite doing it the complicated way yet. Now, let's start again, except with 2 different points. I've kept the point P, 1, 1 the same, but point B is different. It's at 3, 9. I can still find the gradient joining P and B. How would I do that? Well, I'm glad you asked. Let's use the gradient formula. And this time, we're going to join P and B using y2 take y1 on x2 take x1. Let's see, what will we get? y2, 9 take 1 over 3 take 1, which gives 9 take 1 is 8, 3 take 1 is 2, gives me 8 over 2, which cancels to 4. So the gradient of the line joining the points P and B, that red line on the graph, is 4. Well, let's start again. Let's take the point P and a different point now, the point C. Notice they're a lot closer together now. I'm getting closer and closer together, so my line's a bit shorter, but can I find the gradient of the line joining P and C? Well, I'm glad you asked. Of course I can. I'm going to use my gradient formula, y2 take y1 over x2 take x1. What's y2? y2 is 4 and y1 is 4. x2 is 2, x1 is 1. So I'll end up with 4 take 1 over 2 take 1. 4 take 1 is 3, 2 take 1 is 1. So I get 3 over 1, which cancels to 3. So the gradient of this particular red line here, the slope or the gradient or the steepness rating if you like, is 3. Let's try another 2 points. This time I've still got my point P, but this point D is really close to P, and it's 1.1 up 1.21. That actually lies on the parabola. Wonder if I could actually, it's really hard to spot it, but you can see that there is a tiny little red line just between those 2 points. I want to find the gradient of that tiny little line. Wonder how I could do that. Well, I'm glad you asked. I've got a formula for that. The gradient formula. Let's use that. Now, there's my y2 and y1. So it'll be 1.21 take 1 over 1.1 take 1. Now 1.21 take 1 is 0.21. 1.1 take 1 is 0.1. If I actually put that into the calculator, that'll give me 2.1. And the gradient of that tiny, tiny little line there is 2.1. So let's have a look at all of those 3 different answers. Sorry, 4 different answers. Got to learn to count, don't I? We're looking at our 4 answers. When the points were quite a way apart, first one there from P to A, the steepness or the gradient of that line was 5. The next one was 4, the next one was 3, and the ones that were really close together was 2.1. Well, let's just backtrack a bit. I want you to actually think of a curve. If I'm traveling along this curve, I'm traveling downhill, 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 and I actually start on a steep downhill journey and I'm starting to flatten out until I get to somewhere in this region here where it's perfectly flat at one instant in time, and now the journey is uphill. So the gradient was negative, 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 negative because it was downhill, and the gradient becomes positive because it's uphill. But at that point there, it's flat, so it's 0. So as I'm going back up, it's uphill, and it's getting steeper and steeper and steeper as I climb. Okay, so I just need to keep that in the back of my mind. What I want to be able to do is find out how steep my parabola here is at the point 1, 1. And the way we do that is at 1, 1, we draw a tangent in. Now it's pretty hard to draw a tangent in by eye, but there's a tangent there, or an attempt at drawing a tangent. Let's actually put in the correct tangent. Looks like that. That green line is my tangent to the curve at 1, 1. And remember, a tangent is a line that doesn't actually go through the curve, it just touches it at that point. So that's my tangent at 1, 1. Can I find the gradient or the steepness rating of that green line, of that tangent line? Well, of course I can, and I'm glad you asked. But I'm not actually going to use a formula for this one. What I'm actually going to do is I'm going to use rise over run because I've actually got it drawn in. Now, I'm telling you the tangent is 2, but the way I could have done that was I could have done this. Let's take maybe that point there, that point there. Look at that, the rise, gone up 2 units, the rise is 2. The run, I've gone across from 3 to 4. Run is 1, 2 over 1 is 2. So I get a rise over run of 2. Now what I want you to be able to notice here is, well, the question I'm asking is, what's happening as the 2 points I had on the graph got closer and closer together? When I use the points P and A, I got a gradient of 5. When I move the points closer together and I use P and B, I got a gradient of 4. P and C, the line joining those, gave a gradient of 3. When I put the point D really close to the point P, I got a gradient of 2.1. And if you look at all of these red lines, as the points get closer and closer together, the red lines are getting closer and closer and closer to having the same steepness rating or the same gradient or the same slope as my green line. Now obviously I could have gone closer. Instead of using the point 1.1, I could have used the point 1.001 or something like that. The closer I move my second point to the point 1, 1, the closer my gradient will be to the actual gradient at 1, 1. How steep it is at 1, 1. If I can find how steep it is at 1, 1 without drawing tangents in, I'm actually differentiating and finding at that instant the gradient of a point on the curve. And that is what differentiation is all about. Being able to find the derivative or differentiate is being able to find the gradient on a curve at any point in time, because it will continually be changing. So the steepness rating will be changing. So using calculus, we can find out at any moment on that curve, we could find out the steepness or the tangent, the steepness or the gradient of the tangent at that point, or the slope of the tangent at that point. Now, there are two different ways we can differentiate by first principles. We're only covering one. Before we cover the method, just want to remind you, in case you see the word secant, a secant is a straight line that passes through two or more points on a curve. So if I actually had a parabola, took a point there, took a point there, and joined them, that line is called a secant. If I took two different points and joined them, that's also a secant. A secant is just a straight line that passes through two points on a curve, and sometimes it can pass through more. Now, let's consider a curve. I don't know what it is. I'm just going to say that the curve's y equals f of x. And y equals f of x just means that this is something that we're going to graph. Y is equal to something with x's in it. It could be y equals x squared, y equals 2x plus 3, y equals x cubed plus 4. It's just y equals something with x's. I don't know what the equation is. I don't care. On this equation that I've graphed, I'm going to choose two random points. Doesn't matter where I put them. I'm graphing them over in this section just so it's a little bit easier to draw. Now, the first point I'm going to call x, y, because I've actually gone out x, so I've gone out x and up y. And remember, another way of writing y is f of x. They are interchangeable. If you see f of x, that means the same thing as y. Now, I've now got the point x, y, because I've gone out x, up y, but I'm not writing it as x, y, I'm writing it as x, f of x. I want to go out to this point here. And when I'm doing that, what I do is I say, okay, originally I went out x units. Let's go out another h, so that when we get to this point here, we're out x plus another h. So we're out at x plus h. And if I'm out at x plus h, that's the x value of this point here is x plus h. The y value, instead of being f of x, because my point is no longer called x, it's now called f of x plus h. What that actually means is, out here at x plus h, if I plug x plus h into the equation of my graph, it'll tell me the y value, which is f of x plus h. If you don't quite get that, not essential, providing you can remember that that's x plus h, and then you just write this bit down. The y part is obtained by using x plus h. Now, let's join our two dots. Can I find the gradient joining those 2 points? Well, I'm glad you asked. I can. I can use a formula called the gradient formula. Now, y2 take y1 on x2 take x1. This point here, I'm going to call x2, y2, and this point down here can be x1 and y1. So that's what I'm going to use for my values. So when I actually plug them in, I'll end up with, for the y2 take y1, I'll get the y value of my second point, which is f of x plus h, minus the y value of my first point, which is f of x. On the bottom, The x2 take x1 is x plus h, take away x. So there's my bottom part. Now let's look at the top part of the fraction is messy. Top part of the fraction we can't do much with. Let's leave it. The bottom part we can. I've got an x and a minus x. Well, they're just going to cancel each other out. So I've really only just got a h left now. So that's what I have. That gives me the derivative of that red line, or it gives me the slope of that red line is a better way to say it, not the derivative. It gives me the slope of that red line, or the gradient of that red line, using this formula. I don't know what f of x and f of x plus h are, or h is, but if I did, and I could put number values in, I'd have the gradient. Now, the next thing, what would happen if I pulled this point here in closer and closer and closer? The closer the point got, the smaller h would become. So h would be getting closer and closer and closer to being a distance of 0. So what I'm going to do is I'm going to say as h gets closer to 0, and that's limits, as h gets closer to 0, I still have the same formula. But the answer to that formula, remember from what we did earlier, the closer these points get together, the closer my answer is going to be to being the gradient at that point. And I could find that by drawing a tangent in. So let's just read what I've written here. It says, as h gets closer to 0, the 2 points get closer together, and the gradient that we find joining those 2 points, that gradient gets closer to the actual gradient at this point. Now, instead of writing m equals, let's introduce the terminology we use for calculus, and we're going to write f dash x equals. Now, some people will say f prime x. I've heard people say f dash x. I'm going to use f dash because it just looks like a dash, but f prime is more correct probably. But so our derivative at that point there can be found using this complicated looking formula. And if I use this complicated looking formula, I'm differentiating by first principles. Well, I know you're excited to try an actual question because it looks like fun, doesn't it? Let's do it. But before we do, here's just a little simulation where you can see what I have is my point A. That's the tangent. Now I know that the tangent has a gradient of 2. So at that point there, at point A, along this curve, at that one point, the curve has a steepness rating of 2, has a gradient of 2. If I look at my red line, those 2 points, when I join them, have a gradient of 4. But if as B moves closer and closer and closer to A, the gradient of my red line will get closer and closer and closer to 2. Let's have a look. Let's start moving it a bit closer. Now you'll notice B is moving closer, and as it is, see how that answer is getting closer and closer and closer to 2. And as it gets super close, the answer should get very close to 2. And you can see I'm getting closer and closer and closer in. As B gets closer and closer, and I got very close, not quite, I could have got closer, but I got down to 2.01. So the closer the points were together, when I make the distance between them, and the distance between them is h, when I make the distance get closer to 0, the answer for the gradient of my red line is closer to the actual gradient of my tangent, which is the gradient at point A on the curve. It's pretty exciting, isn't it? It's cool stuff. Let's go and do a question. Now, before we do the question, of course, I need to just rewrite the formula. That's our formula to differentiate by first principles. Righto, let's go. Now, to differentiate by first principles, you actually have to have a graph of some kind. Now, we're not drawing the graph. We don't draw the graph when we differentiate by first principles. We use that formula. But here is what we would have to graph for question number 1. And this is basically saying if you considered y equals 2x plus 3, what would the steepness be at different points along that line? Now it's a line. Steepness is always going to be 2 because the gradient is 2 and the gradient matches up with the derivative. But let's see how complicated it gets when we actually do this by first principles. You will always have y equals 2x plus 3 for this question because that's the question, but we don't think of it as y, we think of it as f of x. So we always have that given to us. The next bit is to figure out what f of x plus h is. Now the way you do that is you look at what the question that was written is. And next to that, you'll rewrite the question that was given to you, except everywhere you see the letter x, you always just put x plus h in its position. So see where I've got the x's? This is exactly the same, except I've put an x plus h wherever I had an x. And it's always a safe idea to put the x plus h in a bracket. That way you don't accidentally make any mistakes. Now when I look at this particular question here, I can look at that and say, oh, 2 can times into that bracket there. So let's do that. If I do 2 times x and 2 times h, I end up getting 2x plus 2h, and I've still got that plus 3 hanging around on the end. So I figured out what f of x plus h is. Now, here is my formula. So just write the formula down. Now, when you're looking at the formula, everywhere you see f of x plus h, I can now replace it with 2x plus 2h plus 3. In the formula, where I see f of x, I can replace that with 2x plus 3. So I've used a set of square brackets so I can sort of try and identify the two parts. This bit here is f of x plus h. What was f of x plus h? 2x plus 2h plus 3. 2x plus 2h plus 3. In the formula there's a minus sign, so I put a minus there. In this set of brackets I have what f of x is. If you go up to the question, f of x is 2x plus 3. So I have 2x plus 3. The formula says put it all over h, so it's all over h, and the formula has limit as h approaches 0 at the front. I haven't changed that. I've just substituted f of x plus h with an expression and f of x with an expression. Now I'm going to break this down a little bit further. Looking at this part here, and at the top only, where they've got my two brackets, let's see, are there things there that I can add or subtract or do things with? Well, actually, I've got a 2x here and a 2x here, and there's a minus between them, so 2x take 2x, that drops out. I've also got a plus 3 in this bracket and a plus 3 in this bracket, and they're being minused. 3 take 3 drops out. Well, that's good. So my 2x's drop out, my 3's drop out, and all I'm left with is 2h on the top of the fraction. So I end up with the limit as h approaches 0 of 2h over h. Well, now that I look at that, my h's can cancel each other out. And I'm just left with the number 2. I don't need to worry about limit as h approaches 0 anymore because I just end up with number 2. You've just differentiated from first principles. So the derivative of f of x equals 2x plus 3 is 2. And we write it like this. We say the derivative of f of x, that f prime x or f dash x, the derivative of f of x is equal to 2. What that actually means is that if we took, and the original was y equals 2x plus 3, which is a line that goes through 3 with a gradient of 2, something like that. If I took that line there and I travelled along it, at every single point along that line, I have a steepness rating of 2. That's all we've done. Would have been far quicker just to look at the original question and go, oh, the gradient is 2. Done. But we're doing it by first principles. And we're starting with a line we can find the gradient of a line. What about when it's not a line, when it's something like a parabola? So let's do our second example, because I know you're excited to do it. Here we go. We've got f of x is equal to 2x squared plus 5x plus 4. So that's really y equals 2x squared plus 5x plus 4, which is a parabola. Now, I always get given f of x in the question. That is always provided, but f of x plus h is not. So I need to rewrite this question. Everywhere I see the letter x, I'm putting x plus h in its place in a set of brackets. And that's exactly what I've done. So let's just go back over this. See where I have f of x? I wrote f of x plus h in brackets. Instead of 2x squared, I've got 2x plus h in brackets squared. Instead of plus 5x, I've got plus 5x plus h in brackets. Plus 4 is written there, so I just continue the plus 4. There's no x's with it, so nothing changes with the plus 4. Now, when I have this here, I can actually expand that. If I've got x plus h squared, I could smiley face it, or I could FOIL it. Either technique is fine. I'm going to smiley face it. X times x, x squared. Times them together, x times h is xh. Double it, because it's a doubly happy smile. 2xh plus h times h, h squared. So x squared plus 2xh plus h squared is what that bracket there becomes. This second bracket, everything is times by 5. So instead of 5 bracket x plus h, I'll end up with 5x plus 5h. So when I do all of that, I'll just end up with this. Expanding the x plus h squared gave me x squared plus 2xh plus h squared. I've still got a 2 in front of it. Now that's going to have to times to every part. The 5x plus 5h I've written down, the plus 4 stays there. Let's multiply every part in this bracket by 2. So 2 times x squared is 2x squared. 2 times 2xh is 4xh. 2 times h squared is 2h squared. So that'll give me 2x squared plus 4xh plus 2h squared plus 5x plus 5h plus 4. What a mess! But you wait to see what happens. You're going to be really excited by this. It's just going to be marvelous the way things drop out. Here's our formula. That's the formula that we use every single time when we're differentiating by first principles, except I need to replace the f of x plus h with something I prepared earlier. Well, here's a bit of a messy expression I prepared earlier. That's also equal to f of x plus h. So over here, where I see f of x plus h, I'm not going to write that anymore. I'm going to write 2x squared plus 4x plus 2h squared plus 5x plus 5h plus 4. Where I see f of x in the formula, I'm going to write 2x squared plus 5x plus 4 because that's equal to f of x. So I actually use square brackets for each part just so I can clearly identify each bit. That's my f of x plus h from there. This bracket has my f of x from there. So realistically, I now have a look to see what happens. See, I've got a 2x squared in this bracket and a 2x squared in that bracket, and they're being subtracted. Notice I've got a 5x, a plus 5x and a plus 5x, and they're being subtracted. And I've got a plus 4 and a plus 4, and they're being subtracted. Well, that's good. I've got things here that are going to cancel. So the 2x squareds are going to cancel when I subtract them. The 5x's will cancel when I subtract them. The 4's will cancel when I subtract them. What am I left with on the top? I'm left with a 4xh, a 2h squared, and a 5h. That's all I'm left with. That big long mess there, quite a lot of it just disappeared. So you will always get bits that disappear, and then once we can write down the leftover parts, look at the top of the fraction and say, is there a common factor? Well, there is. It's a common factor of h. So let's take out our common factor of h. If you take out h, you'll be left with 4x. If you take out a h, you've still got one h left, so you're left 2h. Take out your h, you're still left with a 5. Now I've got something that cancels my h's. Let's cancel them, which means I'm just left with 4x plus 2h plus 5. Now, let's let h actually equal 0, even though it's not. It's, it's something like 0.0000000000001, something tiny, or even tinier. Let's just say, let's see what happens if h equals 0. The answer is going to approach 4x plus 2 times 0 is 0, so that part's just going to drop out, 4x plus 5. And there's your answer. Now, what does that actually mean? Well, the derivative of f of x equals 2x squared plus 5x plus 4 is equal to 4x plus 5. That actually means this. If I graph 2x squared plus 5x plus 4, I don't know what it looks like, I don't care, that's my pretend graph. This rule here that I've just found means for every x value on the curve, let's say I went to here, and that was 1, and that was 2, and that was at 3. Let's say at an x value of 2, I come to my rule, 4 times x. 4 times 2 is 8. 8 plus 5 is 13. At that point on the graph, the gradient of the tangent is 13. It has a steepness rating of 13. If I went out to 3, it means I'd be there. At that point there, 4 times 3 is 12. 12 plus 5 is 17. I'm getting steeper. And as you go out, you'll get steeper and steeper and steeper, and these answers will get bigger and bigger and bigger. So what you can see is that what we're actually finding is a rule that lets me find how steep my curve is at any point in time. All I need to know is the x value of that point to find how steep the curve is. And we'll talk about this in a lot more detail when I get back. Let's try another example. No, let's not. Let's do some questions. Do the best you can. Break it down into finding f of x plus h first. Have fun!